Okay, so here's how the next 2 days are gonna play out. Go through and explain the lab today, we'll start it today. Then you got the quiz tomorrow, and then after the quiz, we'll finish up the lab. So this lab will not be due until Monday, all right? So it's a kind of complex 2-day lab. But oddly enough, it all hinges on the idea that force net equals force applied plus force opposing. So here's what you're gonna do. First part of the lab, you're gonna take a 500-gram mass, and you take a scale, make sure it's reading 0 in the vertical direction, okay? And you're gonna take a 500-gram mass, and you're gonna hook it up. Now, what should the reading be if I'm holding up a 500-gram mass?
Yeah.
4.9 newtons, okay? And it's 4.89, okay? Pretty close, right? So, right now, what's the sum of all the forces?
0,
0. Why?
because
It's not moving or accelerating.
Force tension is
It's
the
not
same.
accelerating. Okay? It's not accelerating. Is the Earth pulling down on the 500-gram mass?
Yes.
Gravity. What's this thing doing?
It's pulling up on the earth.
Pulling up on the Earth. Okay? So that's an action, force that through a distance kind of thing. Okay? Is the weight pulling down on the string?
Yes.
So the string has to be
Pulling up on
pulling
the
back
weight.
up. Cool. Now, here's the question. I'm going to take this and I'm going to accelerate it upwards. Okay? So there's 3 things can happen to the reading on the scale. It can increase, it can decrease, or it can just stay the same because gravity is the same pulling down at 4.9 newtons. Okay? Those are your 3 options. Increase, decrease, stay the same. Gap Sean. What's it going to do?
Stay the same,
Stay the same. Why?
because net force is 0.
Okay? Everybody cool with that answer?
no.
No.
Who's not cool with it? Colin, why are you not cool with it?
Because it's similar to the balloon thing, where you're applying an upward force, like where the balloon was tied to the weight on the scale. I think it'll be similar to that, where there's an unbalanced force, so the weight, or the reading will be less.
Will be less.
Wait, you're pulling up on it, right?
I'm going to accelerate it upwards.
Okay, I think it'll be more.
Why?
Right. Because you're actually I don't know.
Colin?
I want to say it stays the same
Okay.
because even though you're accelerating
This-
upward, the mass should pull on the string with the same amount of force.
You're pulling up the
Yeah.
constant velocity. Is that
No.
It's
No,
accelerating it
accelerating?
upwards.
Okay.
Well, Stanley.
So since you're accelerating the whole system upwards, I think it'll weigh more. Like it'll go up.
But he's not.
The number will go up.
He's not
He's
pushing on the bottom as well.
Oh, I'm not
He's
pushing up on the bottom.
He's
I'm just-
accelerating the
That's
whole
what I mean.
system.
I'm just going to do this.
Yeah, but the whole
And so
Let me show you what the action's going to look like. Okay?
he just throws the
So I'm
weight
going to be
away.
like this.
But
Okay? And I'm going to do that.
the weight has inertia, so it wants to stay in the same place.
Ooh,
it wants to
yeah,
retain
good
that,
point.
and then to accelerate it, you have to exert a force on it, which makes it accelerate.
No, it would
So,
increase.
so the weight
It would
wants
increase.
the weight wants
Because
to like
there's-
stay there.
I forgot about
And you're-
inertia.
and You're
Yeah.
pulling, you're
Because
pulling
there's
up, so there'll be
That's
tension
assuming
there,
he goes
so
fast enough to
a
go.
greater force.
That's assuming he goes fast.
So you think
enough
the
to
force
go.
on the reading on the scale is going to go up?
Yes.
Yeah.
Gap Sean? You seem quite passionate about your answer. Go ahead.
I said it's gonna stay the same because you're accelerating the entire system, and the new that tool is gonna only be measuring the weight of the 500 gram mass.
Okay?
I agree with Colin's answer more. I feel like it
I
should.
think the weight will increase
Why?
because like the inertia wants it to like stay. So when you pull up, it's gonna. I don't know.
Require more force than just
Mhm.
the gravitational pull on it.
Anna? Increase, decrease, stay the same. You got a 33% shot.
I think it'll increase.
I think you're right.
I
Now-
think it's gonna go down.
Let's start with
He
this.
finds a way to pull on it, and the whole weight just disappears.
It's just
Let's
It
start with
actually
this,
decreases
okay?
to 0.
Let's start with this idea. You're gonna have three forces: force applied, force opposing, net force. The first thing we have to establish is that what is the scale reading of those three?
The
Or actually, never mind.
No, Danny.
Yes.
If this was giving you the net force, right now, what should that scale be reading?
Zero.
Why?
Because nothing is accelerating.
It's not accelerating. So right now, the net force is zero. So if this was reading the net force, what should the scale read?
0.
Zero. Scale's reading 4.89. So it can't be
Net force.
the net force. So that leaves us either the applied force or the opposing force.
Opposing force.
Applied. It's applied.
Danny, what is it?
Applied force.
Beautiful. Why?
Because
agree with
if it was a opposing force, it would be negative.
Yeah, because, Will, let me ask you this. What if I cut the string?
It would read 0.
Yeah. And what would this do?
Fall.
Accelerate downwards?
Yep.
It has room
Yeah.
to fall.
Yeah.
So it must.
So this is the
Applied force.
applied force. Okay? Now, I want to accelerate it upward. So right away, what does your net force not equal?
0.
Zero. Gap, Sean. Are you kind of seeing the light? Okay. So here's the 500 gram mass. When in doubt, draw all the forces acting on the system.
Out.
So you're going to have some force applied. Sometimes that's referred to as tension. It's the same thing. Okay. Then you're going to have some opposing force. Now, what's creating the opposing force? The frictional mafia or the gravity mafia?
Well, both
Grab-
a little bit, but
Well, this is a 0.5 kilogram mass. So remember, the gravity mafia charges $9.80 per kilogram. So if you have a 0.5 kilogram, what's the opposing force?
Half 9.8, 4.9.
4.9. So the opposing force is going to be negative 4.9 newtons. Is that going to change when I accelerate it upwards? No, because that's a fixed value, okay, based upon the mass and the gravitational value of the rock that we're on. So it's basically what's the only thing that I can control.
Force applied.
Force applied, right? I can change the force applied. So if I want it to accelerate upwards, and if you look at force net equaling force applied plus force opposing, that's going to be negative 4.9 newtons. Okay? That's what you have to pay to the gravity mafia. So if I want it to accelerate upwards, my net force has to be a positive or negative value. If I want it to accelerate upwards,
Positive.
that has to be a positive value, which means my applied force has to be bigger than
negative force.
negative 4.9. Okay? So, I take this, it's at 4.89, I accelerate it upward, it goes up to like 5.5, something like that. So, when that goes up, is it because it got heavier?
No.
No.
No. It's just that you want it to accelerate upwards. So not only do you have to overcome the force of gravity that keeps it from falling, you have to add in the additional force it takes to accelerate it upwards. Okay? Makes sense. So the first part of the lab, what you're going to do here is this, and I tell you, you're going to take a 10 Newton scale, or just the electronic version of it, and you're going to do 4 things. You're going to try and move it up at a constant velocity. You're going to move it down at a constant velocity. You're going to accelerate it upwards, and then you're going to accelerate it downwards. Sometimes it's tough to see because that's like a digital reading. So if you want to take your phones and like record it as it moves so you can see like what those readings are, that might make it easier to get like a more precise reading on those values. Then you got a whole bunch of questions to answer. Now, one of the things it's going to talk about is the maximum tensile strength that a cable can have before it snaps. So let me give you an example of that. Try not to break anything. So here I've got the basic Dillon's plastic bag, which I hate with a passion, but I needed it for this demo. And inside of here I have a couple of 1 kilogram masses, okay? So if I lift this up, as I begin to lift it up, is it accelerating?
Yes.
Yes, because it's moving from at rest up to a certain point, right? And the bag holds, okay? Not a big deal. But if I lift up very quickly, what happens?
Breaks.
Bottom of the bag breaks. So if you're tasked with designing plastic bags for grocery stores, again, which I hate with passion, but you have to say, hey, what's the breaking strength of that bag? Okay? Well, what's the average amount of weight that you're going to have in it? When grandma picks it up, what's the average acceleration? Okay? Because you don't want to design a bag where every time someone picks it up, it breaks. But by the same token, you don't want to design a bag big enough that it could stop a bullet at high speed in case, oh, there's an attack, let me put up my grocery bag over my chest, because that's just going to cost a lot of money. So like, how do you strike that balance? So the point of this story being is that whether it's a string, a plastic bag, a steel cable, everything has a maximum amount of tension that it can stand. And if you exceed that thing, it's going to break. So you're going to have a question involving an elevator. Okay? And typically, these vertical acceleration problems are what we call elevator problems, because they're typically either in an elevator, which is what you're modeling with the 500 gram mass, or there's a helicopter. And that's why it's called a elevator. So when you're dealing with these problems, I cannot emphasize this enough. Go back to the idea that force net equals force applied plus force opposing. What's the only time you do not have to worry about an opposing force of gravity?
When you're in
Deep
space.
space.
Unless I tell you you're in deep space, you worry about gravity. All right, go on, give it a spin so we can go over here to the stapler. Actually, I gotta set this back on the pole. Get it off, hold on.
Corn broke it again.
I didn't break anything, I think. I should have just, one sec. This will be easier. There we go.
Okay. So y'all have dealt with this before, you've handed stuff in, but now let's talk about the physics of why it works. So I pull this down, and I let go of it. What does it begin to do?
Accelerate up.
Does it accelerate? So what do the forces not add up to?
Zero.
Zero. So you've got the stapler on one side and a 500 gram mass on the other. Which one weighs more?
The 500 gram.
500 gram mass. How do you know?
Because it goes down.
That goes down, this gets dragged with it. Okay? So this is like Cohen going out on the date, but he has to bring Teague with him. Okay? So Teague is acting as an opposing force to Cohen going out on his date. So let's start with the 500 gram mass. Pretend that the stapler isn't here, okay? Forget the stapler, ignore the stapler, it's gone, it's not there. Right now, what's the sum of all the forces?
Zero.
Zero. So it was a 500 gram mass. So it's the downward pull on a 500 gram mass,
4.9 newtons.
4.9 newtons. So what's the upward tension on the strain?
4.9.
4.9 newtons, right? Negative 4.9, positive 4.9, everything adds up to
Zero.
we don't accelerate. Now, what if I just cut the string? Danny, if I just cut the string, I cut the string, what's the only force acting on that 500 gram mass?
Opposing force,
Which is going to have a value of,
9 point,
no,
or actually,
starts with
negative,
4.
negative 4 point something,
9,
9.
okay?
Oh, I didn't see that. Newtons.
Also put on the board. Okay, so if I just cut the string, the only force acting on it is gravity, and that's going to be a net force of negative 4.9 newtons. So if I have a negative net force of negative 4.9 newtons, and I divide that by the mass, what's my acceleration going to be, Danny?
Negative 9.8.
Ah, beautiful.
Meters
Okay,
per second.
of negative 9.8. So that's if I cut the string. Okay? Now, when I let go of it, what's the force that's making it fall? Gravity. Well, if gravity is making it fall, why doesn't it accelerate at 9.8 meters per second squared?
Because it's got to
Because
drag
the
T
mass
along.
of the mass of the system.
Yeah, we got, well, there's that, and we got to drag T, right? Okay, we're dragging T. So, here's what you want to focus on. Even though this stapler is attached to it, does that impact the gravitational pull on this side?
No.
No, that's still the same. This is still being pulled down at 4.9 newtons. So we're going to call that 4.9 newtons the applied force, because that's what's trying to make the system move. I got a 4.9 newton force going this way. This is the applied force, okay? So, Sean, what's the stapler doing? It's acting as the,
Applied force.
no. This is the applied force.
Oh, yeah, that was opposing.
This is acting as the
Opposing.
opposing force. Because this is like going, whoa, whoa, whoa. The stapler's over there going, whoa, hey, I'm being pulled on, being pulled on by gravity as well. Okay? Gravity's pulling down on this. Now, we don't know the numbers, but would you predict the mass of the stapler to be bigger or smaller than 500?
Smaller.
Smaller. You think it's a lot smaller?
Not a lot.
Not a lot, okay? Because it isn't like it's a huge acceleration, right? So, oddly enough, we're going to look at force net equals force applied plus.
Force opposing.
So, we're going to call this 4.9 newtons our applied force. Okay? That's what's making the system move. We're going to make the weight of the stapler be the opposing force. And the difference between those two is going to be our
Net force.
net force. Okay. Now, the last step is always to get the acceleration. So here's the question. To get the acceleration, do I divide by the 500 gram mass, the mass of the stapler, or the combined mass?
Combined.
Always the combined mass. Always, always, always you divide by the combined mass. Why?
Because the
It starts with, you want to say the I word. Second letter N.
inertia.
Beautiful. Okay? Okay? Inertia. Does the 500 gram mass resist a change in velocity?
Yes.
Yes. Does the stapler resist a change in velocity?
Yes.
Yes. So one way that you can view this is that imagine that I tape the two together and then I apply a force to it. So if you look at F equals ma and you combine these two masses together, they both resist a change in velocity. This wants to stay at rest, this wants to stay at rest. They both resist a change in velocity. So that's why you have to divide by the combined mass of the system. Okay, so Cohen, stop that camera again, let me hand out the lab, and then we'll get started.